Okay, so in this video, I want to go through some more integration by parts examples. Now, I recommend you go for a previous video of mine where I've done some different examples in a bit more detail. But we're going to go through some more questions here. So let's start with integrating x squared e to the x dx. Now again, you can see that we've got two functions of x. We've got an x squared, and then but this time we've got an e to the x. So if I write out my Lie8 again for integration by parts, I can see that my algebra term is x squared, but this time I have an exponential term in the form of e to the x. A comes before e, so I'm going to set u is equal to x squared, and my other term is going to be dv by dx is equal to e to the x. Now differentiating u, I get du by dx equals to 2x. Integrating dv by dx, well, integrating e to the x is just a standard integral which returns e to the x again plus c, so it just returns itself. Now if you recall the integration by parts formula, I is equal to uv minus the integral of v times du by dx dx. Now let's replace the terms in this formula with the terms we've just found. So this means my integral I is equal to uv, so x squared e to the x, minus the integral of v, which is e to the x, multiplied by du by dx, which is 2x dx. Now I'm going to tidy this up by taking any constants outside of my integral. So this is x squared e to the x minus 2 lots of the integral of x e to the x dx. All I've done is just rearrange the order inside that integral. Now again, you can actually see we've got two functions of x being multiplied together. So this means we're going to have to use integration by parts twice. So my new function, we've got f of x and g of x. Okay, so using integration by parts once, we found this term. And it's really common to not add this term in once you apply integration by parts again. So I'm just going to highlight it. Using Lie8 again, I can see that my u is going to be equal to x because a comes before e. dv by dx is going to equal to e to the x. Differentiating u, we get 1. Integrating dv by dx, we just get e to the x again, and technically we have a plus c. Okay, so that means that my integral is going to equal to what I had originally, so that x squared e to the x. Now take away 2 lots, and then this is where I'm applying integration by parts again in this section here. So minus 2 lots, applying the formula u times v, so x e to the x minus the integral of v e to the x times by du by dx, which was 1 dx. And I've just put curly brackets to show that this is the part where I've applied the integration by parts formula again. So we get x squared e to the x minus 2 lots of x e to the x minus the integral of e to the x dx. Now we know from earlier that integrating e to the x just returns itself, and then technically an integration constant. So we get x squared e to the x minus 2 lots of x e to the x minus e to the x. I'm also going to have a plus c because it's indefinite integration, meaning we have no limits. Now again, tidying this up, we're left with my integral is equal to x squared e to the x. Now we have a minus 2 on the outside, so it's really common again to forget to multiply this out properly, but that leaves us with minus 2x e to the x plus 2 e to the x, because this time we've got a double negative, and plus c. So that'd be acceptable as a final answer. If you wanted to take it one step further, you could factor out e to the x, say well that's the integral is equal to e to the x times by x squared minus 2x plus 2, and let's not forget our plus c. So both of those are equivalent, and that's my final answer. And we want to integrate ln x with respect to x. Now this is slightly different because we don't actually have a product inside the integral. Okay, for these types of questions, you just have to remember, in order to integrate ln x, you have to use integration by parts. So what I can then do is just rewrite this as integrating ln x times by 1 dx. Notice the integrand, so the thing inside the integral, has stayed the same. Now using Lie8, I know that logs comes first. So my u is going to equal to ln x. My other term is going to be dv by dx. That's just going to be 1. We know du by dx is equal to 1 over x. Integrating dv by dx, we get x, and then technically that integration constant. Now substituting this into my integration by parts formula, I get my integral is equal to u times v, so x ln x, minus the integral of v, so x, times by du by dx, That's x ln x minus, well, these x's will cancel. So we've just got the integral of 1 with respect to x. So my integral is equal to x ln x minus x, and let's not forget to add that integration constant. And that's my final answer. So this time I want to integrate between 0 and pi over 3. So we've got a definite integral this time because we have limits. So we don't have to worry about that plus c. Then we get sine x ln of sec of x. Now notice I've put the sec of x inside the square brackets to show that it's inside that log function. Now this is slightly more difficult because you can see we've got, well, one function of x. Well, this is technically also a function of x. And then we have another function of x inside of that. But on the outside, the product is between sine x and this ln function. So that will be my f of x. This will be my other function, g of x. Now we stick to exactly the same process. I know that log comes first in Lie8. So my u is just going to equal to ln of sec of x. And then my dv by dx will be my other function. So that's just going to be sine x. So du by dx is going to equal to, well, we've got a log function or an ln function. So that means we have to do 1 over the inside times by the derivative of the inside. So the derivative of sec of x. Now this is applying the chain rule for differentiation. Now if you don't understand why I've done this step, then I recommend revising that topic. But if we simplify that down, we get 1 over sec x. Now this is just a standard derivative, which is equal to sec x tan x. So the derivative of sec x is sec x times tan x. So cancelling through the terms, I get that my du by dx is equal to tan x. Now I'm just going to highlight that so we don't lose track. And then I'm going to integrate my dv by dx. Now if you remember from the previous video, when we're integrating sine and cos, we've got a trick. So I'm integrating sine, so I want to go anti-clockwise. So that's going to be negative cos x plus c. Now if I substitute these terms into my integration by parts formula, I get that my integral is equal to u, which we found was ln of sec of x, times by my v, so that's going to have a negative, times by cos x, minus the integral of v, so that's minus cos x, times by my du by dx, which is tan x. Now again, it's a really common mistake to mess up with this double negative here. So just remember, we're substituting in v, and we're also taking away due to the integration by parts formula. So let's tidy that up. We get minus ln of sec of x times by cos x. Now let's not forget, because we're doing definite integration, we're going to have some limits. So if we remember from above, my limits were 0 and pi over 3. So So that's 0 pi over 3. Okay, so tidying things up, we've got double negatives. So I'm going to take that out. So that's going to become a plus the integral of cos x. Now, just from repetition of questions, you'll start to realize that whenever you see a tan x, 9 times out of 10, you're going to want to rewrite that as sin x over cos x dx, which turns out to be quite helpful because now I can cancel through my cos x's. So tidying things up even more, we get minus ln plus the integral of sin x dx, which we found earlier is negative cos x using my trick. So we get that's minus ln of sec of x times by cos x, take away cos x, and then all of that is evaluated between 0 and pi over 3. Okay, so that would be my indefinite integral, but now because we have limits, we need to evaluate that. So that's going to be minus ln that was ln of sec of x, wasn't it? Times by cos x, that's minus ln of, now let's rewrite sec as 1 over cos. So 1 over cos pi over 3 times by cos pi over 3 minus cos pi over 3 take away, now evaluating the lower limit, that's minus ln of 1 over cos 0 times by cos 0 minus cos of 0. Just to be clear, originally we had ln of sec of x, so the sec of x was inside the ln function, and we rewrote that here. So this is all being multiplied by cos x. I just miswrote with my square bracket. So evaluating that, cos pi over 3 is equal to a half, so that's going to become minus 1/2 of ln, well, we've got 1 divided by a half, so 1 divided by a half equals 1 times 2 over 1, which is 2, so that's just going to be ln 2 minus a half, that's my first bracket, minus, well, we've got negative ln 1 over cos 0. Cos 0 is just 1, so that's going to be minus ln 1. Again, cos 0 is 1, minus 1. Well, ln 1, again, just from repetition of questions, you'll start to spot things like this by 0. Or you could just put that in your calculator. So tidying things up, we get minus a half ln 2 minus a half plus 1, which leaves me that my integral is equal to minus 1 over 2 ln 2 plus a half.